Hello everyone, welcome to my shop. I'm Robin. Today I'm going to discuss the Deckel Clone that I purchased. This is a single lip tool grinder or D-bit grinder, or Deckel Clone as they're called. Very handy tool. My purchasing this is a direct result of seeing Stefan Gottsvinter use his, and also from the Tool and Die Guy, his little series of showing various aspects of operating a single lip cutter. I said, you know what, I need one of those. I do lots of cutter grinding just using the surface grinder, which works, and as long as you have enough things to manipulate the tool, you can do quite a few things on there. But this is just a lot handier and just really quick. So I'm going to cover just some of the aspects of why I picked this particular one, and a lot of it's going to cover modifications that I'm doing to it. And this is just number one of probably a series of many that I'll be doing showing improvements to this. I consider this to be a pretty good Chinese kit, as most things from China. The quality of this in general is pretty good, but as in most things, there's some things that are lacking for the level that I would like it to be operating at. So I'm going to be covering what those things are. And this particular one is going to be on the replacement of the main shaft and increasing the stroke length of the tool feed of the main shaft, and changing the entire way that the main shaft is stopped as far as rotational angle. So let's dive in. So as I mentioned, I'd like to give a shout out to Stefan's channel, and also to the Tool and Die Guy. I'll put links in the comments for those guys. Both excellent channels. And also Tom Lipton. Sometimes when people have a lot of subscribers, you kind of forget, but give Tom Lipton a shout out. I doubt there's anyone that's watching me that isn't already watching Tom, but can't hurt to give Tom a shout out also.
Okay, this particular unit is from Shar's Tool. I picked this for several reasons. One was that it looked like it was made in the same factory as the one that Stefan is using. Another big item is that it has 5C collet. It has a ball bearing spindle for the tool rotation, and it came with all the accessories. The sliding 5C collet for doing end mill flutes, the tool holder for doing lathe tools, and the drill grinder comes with 5 collets, belt, comes with the wrench for the wheel adapters, and so yeah, it comes well equipped. I think that as far as overall quality, the Grizzly unit, which I was also considering, is probably a higher quality unit because it's made in Taiwan, but it would cost over double what this one does because none of the accessories are included. So by the time you buy all those accessories, assuming you need them, you're talking being well over double the cost of this. This was in the $975 range for the base machine, and I consider I got my money's worth. Lots of things need to be fixed. Don't buy this thinking you're going to get a Deckel class unit. It's not, but in general it's made very well, and all of the things that are somewhat lacking are relatively easy to fix. Okay, you're seeing this with some of the modifications already done. This section here, this spacer, is for the extended travel. This is the travel this way of the whole slide. So this thing moves in this direction, goes either direction side to side with the hand crank out here. And normally it's a knob, just a knob here, but I put a crank on here because now I have an 1 7/8" of travel. Normally this shaft doesn't poke out this far. It only has like a 1/2 inch of travel. And right here is the knob that controls the amount of how far it comes in. So there's a stop here that stops this to come in for your infeed into the wheel. So in the process of this, as I described, I'll describe in the video, I decided, since I'm replacing this shaft, the shaft that came with this was undersized, I'm going to move this arm out here where it's a much longer moment arm, and just a easier place to put it. And I have a place here for an indicator, and that indicator is actually the exact same distance from the pivot to where the indicator touches as from the spindle axis here to here, such that that's a direct readout. So 1,000th there would be 1,000th here, so you can actually use that for controlling feed. In order to do that, this whole mechanism here, before I go there, all these handles have been replaced. The Chinese handles have been replaced with Kip handles from Germany. They just have a nicer feel, and they're prettier, and they just make the machine look like $1 million, and it feels like $1 million when you're using it. So over here, in order to have this stop, I made a hardened and ground piece of A2 with 3 jack screws and 3 clamp screws, and that lets me level this plate so that it's true to the travel of the shaft. And then the ball on the end of this has a silicon nitride ball pressed into the end. And the reason this is so wide is because the indicator comes down and hits on here also. So that's why that's there. And then that aluminum arm is just longer. And this is kind of handy because you can actually grab this as you're operating the machine and use this for pivoting the machine. I need to put a spring on this to counterbalance it, but it's actually not that bad to work without the spring. So this locks it, and you're going to see me redoing the bushings on this, and redoing the shaft is the main things we've done on this. Just in general, this thing's pretty well made. Lots of things like the degree markers and stuff aren't the best. The degree wheels are okay, but the actual markers aren't the best. So one thing I strongly suggest is getting extra wheel adapters, and I'm going to typically only use super abrasives on here. Main reason being that you end up with very little abrasive dust on the machine. You have a lot of swarf from the carbide and the steel, but not actual grit from dressing a wheel all the time and the wheel breaking down. So I have CBN cutoff wheel, CBN face wheel, CBN OD wheel, diamond cutoff wheel, diamond face wheel, diamond OD wheel, and then on the machine I have, which is my favorite, is a 600 grit face wheel. And that thing cuts really nice, and even though in theory you're not supposed to grind steel with diamond, it does a really nice job, and that 600 grit cuts quick enough to not be ridiculously slow on removing material, but leaves a really nice finish. So that's kind of my go-to. If I was going to tell you to buy one wheel, that would be it. Now, one thing that's really important is make yourself a dedicated wrench for changing the wheels if you're going to do this. So this is an M8 bolt, which is the threads of the puller threads. This push rod is because there's really nothing to hit. If you just put an M8 bolt in there, you're actually crunching up the M6 threads that are the threads of the bolt that holds the adapter on. So this is the wrench size. So a tool change is literally just pop this loose. Let me get this out of the way. Pop the screw loose, give it a spin. It's one of the advantages of having the T-wrench. One of the things I did here is put a hardened washer on the screw. That saves a lot of wear and tear. It goes out and bears on the full diameter, so it doesn't chew up and get nasty in the wheel adapter. And then you just thread in your puller. I mean, most people know about this. And it pops the wheel off, and there you go. You're ready to rip. And you can just quickly, a matter of less than 30 seconds, you've changed from one wheel to another for cutting off or OD grinding or whatever. So works really well. Clean your taper, stick back on, use the other end of your wrench, come back in, spin this back in, And these wheel adapters are not listed on Shar's site, but if you actually talk to somebody and say, hey, I want to buy some of those wheel adapters, I think there were some ridiculously low amount of money. They were below $30 a piece. I was thinking, oh, I'm going to have to make some, set up the Tormach and, run a bunch of them. And for what they cost from Shar's, and they're relatively nicely made, just wasn't worth messing with. This is the case hardened shafting. Got a CBN, homemade CBN groove tool, and I'm going to just cut through the hard case here. Then I'll use a regular parting tool to go through. Center height's a little high. I feel just by the Now I'll come in with my regular parting tool now that I'm down below the case. Here's the finish on the hardened linear shafting, which is centerless ground, and you can see the lead spiral. That's the spiral there of how it actually feeds through the centerless wheels. So this is not as bad as it looks. The reason this has this look is because of me rubbing the mating cast iron piece on there and basically burnishing the inside of the cast iron piece. But I want to get rid of this surface finish because this surface finish is going to carry grit and things through. So the smoother this is, the better it'll slide in the bushings, and the better the wipers will work on squeegeeing off any dirt. So now we're going to take the lap, which we have here. This is just a chunk of aluminum that I've drilled through and bored. And I bandsawed through, and then I just used the edge of the bandsaw to put these linear grooves in. And those grooves are just to give place for lubrication to form, to hang, and the slurry to hang. So we'll probably just lap this with some 6 micron. If I need to put any pressure on it, I'm just going to put an adjustable or a toolmaker's clamp on here, parallel clamp, to put the cutting pressure on. So now we're lapping with the 6 micron. We're using a little WD-40 here for our lubricant. Gentle pressure here. I'm just after uniformity and getting rid of the surface finish from the centerless grind. I'm still seeing some spirals here from the centerless grinder. So probably put a little more slurry on here, and we'll give this a continue on this, just a tad more pressure. Nice smooth drag here. That's 1 micron I just put on. I had put on 6 in the beginning. Then we'll take a look here and see what's going on. It's not going to take long to get this down to where that spiral from the centerless grinder is going. So I'm checking here to see what it looks like. As you can see on camera, but that's still there. So I'm going to lap some more on this and we'll come back. Here's the finish after lapping and using some 15 micron diamond film and then some 6 micron diamond film. And yeah, pretty nice finish on there. You might be thinking, like, man, you're really going off the deep end here with this finish on the shaft. You have to remember that on this single lip cutter grinder, this is the lathe bed. This is the heart of the whole machine. The smoothness that this rotates, how snug it fits in the bushings, how well things clamp to it, how long it lasts by not having any or has very, very minimal surface roughness that grit and things can pass under the seals. All those things add up to this thing performing immensely better, and might have been maybe 45 minutes work of lapping and then the diamond film. So the lapping created the geometry, got it nice and cylindrical. It wasn't that it wasn't cylindrical, but we basically got the roundness and the size really good by using the lap. And then once we did that, then we moved to the diamond film, just using WD-40 and a diamond film to get the surface finish.
This is the main block that clamps to the main shaft of the grinder, and these were for O-rings that actually didn't contact very well, and an O-ring doesn't scrape and squeegee off grit. The grit can climb under the O-ring pretty well, so I bought some square cut O-rings from McMaster, and I'm going to remachine this groove to leave a little compression. If I left this just as square, it would be very draggy, it'd be hard to move sideways. So after I machine the groove for these, I'm going to bevel the inside edge of these with a grind wheel to be like a knife edge, so that we just get a scraper contact where it squeegees off the grit on the rails before it has a chance to get inside. So here's a piece of the hardened shafting that we have left over. I've added this screw, pinch screw here. This is the screw that actually clamps it normally. I've added a M4 screw here that I use to adjust it so that when you clamp and unclamp, you get a crisp action, because this has been closed to be just lightly dragging. So your clamping action is always just click, click, very, very quick on grabbing. So I'm going to use this just to go in and groove, open this groove up and to the dimensions we need. Well, I have this groove tool set up with all the offsets and everything. I threw a 1.25" collet, soft collet that I've made, and grabbed a piece of 1.25" stock and made this ring with the groove for the seal. And this is to go on the outside of the casting, get glued onto the outside of the casting, because the shaft was never intended to stick out this side. It didn't have a seal on it anyhow, but since this is going to go in and out, we're going to put a scraper seal on this outside edge also. Here's the fixture that I'm using to put the bevel on the seals. This is just a little bit smaller than the seal. It's got a shoulder back there,
And I'm going to hold the Dremel tool here on an angle with a coarsely dressed wheel and just grind away until I get the bevel in there. So I'll just do a little bit and then go from there. There's just a little bit left there. I'll go until I have a true knife edge, and then it'll be done. There's the wiper seal. You can see how the bevel leaves a knife edge so that there's very little contact area, and it can deform and not get too tight on the shaft. So this will squeeze you off the grit very nicely. Here's the play in the tail with the new shaft that's been lapped. The original shaft was like 2/1000ths under, over 2/1000ths under. So this is still a huge improvement, but that's a good, almost 7/10ths of play there. So I'm going to Mogliese the bushing where I inject the Mogliese epoxy waylining compound into the bore to get a perfect fit. Here's the 25mm bore, original cast iron bore. That hole is where the locking pad goes in to hold the main shaft in place when you are locking its position. I ran a 1-inch tap through there just to get those grooves that it's an 1.16 tap. Those grooves are there to have the Mogliese get a place to actually get in and bond and have some mechanical tooth into the material. And then, as we can see here, we've got the same thing on the far end, the head end, and I've got my shaft, which is all lap polished as you saw before, and it has a layer of mold release on it. So now I'm going to prep these holes, degrease them, and I'm going to use the original hole that was in these for their oil, little oil buttons. I'm going to replace those with an actual grease fitting. It's a little bit more sanitary and grit resistant, and also allows me to use a high pressure gun using a moly molybdenum grease in here, since it's a very close fit. So same thing, I'm going to use that hole as an actual injection port. I'm going to line the holes first, wet the inside with the Mogliese so that it's definitely in and filled everywhere, and then I will also pressurize, put some Mogliese down in the oil fill holes, put a pin in there and use that pin as a piston to push Mogliese in there until it extrudes out the ends to know that I've got a good fit, and then we'll let that cure. There's enough iron contacting on the one edge of each of the ends, one end of each of the bores, to align the pin, hold it roughly in place. And then in between I've taken a carbide burr and gone in and actually opened it up a little bit, so there actually will be a film of Mogliese all the way around, and a few places where maybe the iron will touch, but that's not the end of the world. The iron's fine touching that hardened shaft. Okay, I've got the bores wetted with the Mogliese. Down at the other end here we've got the same thing going on. That's just to make sure that we've got a good intimate contact with the metal, and then as we inject we're just pushing things around. We're not expecting it to climb into every nook and cranny. So it's always a good idea, if you can, wet the surfaces beforehand. There's the shaft in place. I've got the Mogliese liquid injected into the holes, and dry release on the shaft. So we'll just let this cure. I screwed the grease fittings in. I tapped the M6 or the 6mm holes that were in there for the press-in oil fittings. I tapped them 1/4-28 for the grease fittings, and then I threaded these in with some release agent on the threads so that these form a good fit there. And I'll have to take them out, drill through the Mogliese to form the oil get the oil going all the way down to the bushing, and then I'll do an oil groove in the Mogliese. But this will cure for a day, and then we will pull the shaft out, which will be a snug fit. And this is the heart of our grinder. Everything rests on this. I am changing the design of the stop on the grinder, which I think will be more effective and provide a little more functionality on the single lip grinder.
Mogliese is cured, and getting it to break loose initially can sometimes be a little frightening. I actually have a jack screw in here and pressing, and I had to put enough pressure on there that I was a little concerned about the casting maybe popping, and that would have been a real bozo moment when you break your casting in half because you were molding your bearing fits. So fortunately this broke loose with a little bit of pressure. I actually loaded a little bit and then smacked the casting with a rubber hammer at each location to try to get it to free up. So now it's just mad tight but moving. So we'll get it out, and then we'll just lightly dust the inside of the bushings till we get the fit we're after. There's the Mogliese in the bore after pushing the shaft out. And yes, that is a mirror finish, replicating the mirror finish that's on the shaft. If I didn't have a finish that good on that shaft, if I had molded this to that as ground linear shafting, probably would have had disastrous results trying to get it out. In order to do that kind of molding, I would have had to use a much thicker wax kind of build up on the shaft to actually give some clearance in the molding process.
Here we're checking the bow of the shaft as received. So we've got maybe 3/10 there, and if you look here, you'll see I've got the mark there where the high is, and that is with the shaft completely in place. And I'm spinning it here on the end with my wrench, and I'm doing that so that I can actually, as I rub these bushings out a little bit, the Mogliese, that I actually pick a spot where I'm going to have this, and this is basically where it was molded. This only has to go through maybe 90 degrees of max of rotation, so I'm going to preferentially rub this to accommodate that bow so that it's as tight as it can be for the 90-degree rotation that it needs, yet have the minimum clearance.
Let's take a look at the original main shaft system of the single lip cutter. This is the main shaft that all of the entire cutting head rides on. This has to move axially for in and out feed into the wheel, and it also has to pivot rotationally. And this piece is how they control the in-feed, maximum in-feed position by this block. And there's a screw in the casting that you screw in and out with a knob, and this controls how far, when you slide the whole unit into the wheel or rotate the whole unit into the wheel, this controls the stop. And then for the how this thing connects, how it actually works, they've got a nut body here that rides in the casting, has a dog point set screw that rides in this to keep the nut from rotating. So as you screw this shaft in and out, held in the original, this is the original, forget what you see here, this is the original plate, basically just metal on metal, free play is adjusted, and then they put set screws in from two sides, and that's your bearing for controlling the screw. This bolts to the, these holes are added, but this flange bolts directly to the casting, the outside of the casting here. So this, basically the lead screw stays still axially, and the nut moves, and then the nut carries the shaft, and they, the way that they got this shaft connected so that it can still pivot without influencing the screw is they have a little plate here, like not quite a half circle plate, that goes into the groove, and then this bolts on with two screws, two little
hex head screws that bolt in like this and bolt that together. So the casting sits like this. I'm going to mimic my hands here as the internals of the casting. And it leaves this distance right here between my hand, leaves about, at best, maybe half an inch of travel. Well, half an inch of travel is not, in my opinion, is not very convenient. And if I get rid of all this, I can get travel to be the full distance of what's inside the casting. That in-between distance between my fingers there representing the casting is about 1 7/8 inches. So I say, okay, how can I redesign this? And one of the things that comes to mind is, well, you can't get rid of the stop. That's that's an essential part of the unit. But since this shaft is pure crap, and I'm ordering a piece of linear shafting, hardened linear shafting to replace it, I've got material sticking out the far end of the grinder, and that's actually a better place to put a longer moment arm stop that will have more resolution and be a stiffer system. So now all of a sudden I'm free to do whatever I want here in the middle. So we take this and we say, okay, what are we going to do now? All right, well, I need a nut. We'll come back here and we're working with what I'm currently doing. We need a nut and a screw. But now this nut can travel the entire 1 7/8 inches distance. So it can come from here to here, and then obviously the shaft is following it. So in order to have it be axially snug, be able to rotate and be preloaded, in my nut I left a little flange. There's a bearing bore on this side, bearing bore on the inside with a little teeny flange in the center. That flange is about the width of this spacer that I make. So when I run the screw inside here and screw this to the end of the shaft, I made my end shaft have a little relieved section to bear on the inner race of the bearing and a M6 tapped hole. So all I have to do is thread this in, and now I've got something that is axially connected, but this is free to rotate. So it will have no restriction on the sweep in rotation of the main shaft. So that's taken care of. And then by grinding this spacer a little bit thinner than this spacer and keep checking for end play, I grind that spacer until when this is clamped up, these bearings are actually preloaded against each other so that they're firm, but not crushed obviously, but just snugged up so that there's no play in them. So that takes care of that. Then obviously we need the key so that we have our full length travel. And then since I've got all this space, and I said, the nut, since this nut was the same diameter as the shaft, this is 25 millimeter, the bore through the casting is a straight 25 millimeters through the whole thing. So I said, okay, I can make a nut, relieve it so it's only threaded here at the end. The original was 20 threads per inch, so that the dial worked out in inches. So I have a 3/4 20 tap. So I'm using the same hardened material, and you'll see on the end here that the case only goes deep enough that I still have free machining material on the inside of this. So I can actually make this where this is hard on the outside. This is 60 Rockwell on the outside here. So I ground this notch in. Now this, in grinding that notch in, when we've got this case that's got a lot of stresses in it, this went out around about 4 thousandths. And so I literally, you're going to laugh, but I literally belt sanded the bow off of this on the two sides to get the worst of it off. And then just ran the same lap that I lapped the new shaft with, the actual linear shafting. I still lapped it and polished it. I ran that over that to get that rounded up. So this is a nice hard fit. So this piece, then I make my lead screw here, and now this can thread on. It can do the full 1 7/8 inches travel. And the only thing I need now is my spacer that I made for the casting, such that it gives me the room for this nut to protrude out before it runs into the knob, into the end of the threads here. Okay, now one of the things that I wanted to have ability to do was to get the shaft out without having to flip the machine over and access a whole bunch of stuff from underneath. So as I'm getting ready to put this together, I'm saying, whoa, wait a minute.
my original plan was you would take the 4 long socket heads out of here. So I've actually put holes in the knob so that these bolts can go clean through. So you can get this off without disturbing the bearing, screw this completely out, then take your your wrench and go down through the hole here and loosen that to get the shaft in and out. The reason I'm want to be able to get the shaft in and out reasonably quickly is maintenance, and it may be that, you know what, I have an attachment that I'd like to put on this thing where I literally want to pull the main shaft out, take off the traditional single lip cutter system, and put on some other system that's got a completely different mechanism, maybe a specialized drill grinder, or maybe a specialized anything. Basically using the spindle of the machine and this axis of motion as the basis for other grinding attachments. So I want this removal to be basically, really quick. So I'm getting ready to actually put this together and say, wait a minute, if I had this drilled clean through the shaft so that I could get to this screw without taking that off, just remove the preload screw here, put the wrench in, run this all the way up to the nut all the way up tight so that this screw is actually sitting right there, right in the end, because that's the way it sits. This is how it sits when it's all together here. I wouldn't have to do anything. I'd take one screw out, run my long-handled wrench down through, and be done. So I said, well, I'm going to have to go bigger. I'm going to have to put like an M8 in here to make the hole that goes through clear the Allen wrench flats, the cross corners of the Allen wrench. And so I look at this and I say, well, what if I had one of these with, like, maybe what's the tap size of a M5 that I currently have in there? Well, an M4, the wrench for an M4 fits in there no problem. Well, now I need one of these that's got an M4 head for this size wrench and to be in here. So I think, well, I could, make one. I could broach. I have a rotor broach a rotary broaching tool to put the hex in and all that. And then I'd say, oh, well, how can I do this quicker and easier? Here's our screw. One thing you got to remember when you're tapped through a screw like this is you're compromising the strength quite a bit. And this probably would have worked fine if I just tapped it, down enough to get a short M4 in there. But by tapping it all the way through and letting an M4 run clean the full length, I'm ensuring that I've got the strength of both the M6 and the M4. So for the amount of tension I'm going to put on it with this M4, the wrench for this M4, I don't have any worries about it breaking. This is the best place to start a design on paper. It's easy to get a quick idea of what's going on. You can see here I've drawn my thrust washers, my needle roller bearings, my thicker one for the shoulder. I've got my screw shown. I've got relief, getting all the main concepts of the design done. My spacer tube to give me room for the extended nut travel from the 1/2 inch roughly to 1 7/8. My bearing preload arrangement, I went through a couple iterations here of getting the simplest thing, no snap rings, no anything, just be able to get the absolute minimum number of parts and just have it be functional. So we've got our spacer, we've got our rib that's left in here to lock both bearings. By shortening this spacer, I get a contact angle like this, I get a contact angle like this, where this, I can adjust the preload on this. And then initially I was thinking I was just going to unscrew this, like we said, and put a wrench in here to remove the shaft when necessary for maintenance or changing it to a different setup. But now we've drilled a hole clean through so that I can get to our special M6 with an M4 head screw, so that the wrench will reach right down through there. All I've got to do is take my preload screw out at the end, reach down in, unscrew this, bang, I can take the shaft out, put it back in again. Now, sometimes you can get yourself in trouble if you stop just on paper, because some of these things will look good, but CAD now is an excellent place to go and start putting numbers on these things, making the travels work, seeing how much room you need for all these items, making sure things you've drawn out of scale, when you put them in scale, actually can function. So yeah, I'm no
I am a big advocate of CAD, but CAD can slow you down in this conceptual stage. Here's the new lead screw assembly. The screw itself. The original bearing plate, which was just metal to metal, I got a Garlock DU bushing. This is the Teflon lead blind bushings. Very good for slow speed, smooth operation. Bored that out, pressed that in for that. I put a recess in here for our needle bearing, thrust bearing on this side, 2 thin washers, and the needle bearing. On this side I have 1 thick washer because this forms the shoulder to support the loads there. So if I put a thin washer there, the washer would deflect under load and just start to cup, and you'd only get edge loading of the rollers here instead of a better bearing. This still isn't perfect, but for the loads we're putting on this, it's more than sufficient. So this just gets assembled with some lube for the needle bearings, and we'll put those in. Fill this up with some jet lube. This is Teflon filled lithium base grease. Thrust washer. These are hardened. So this basically forms a needle thrust bearing. Put some lube on our shaft here, even though the Garlock bushing can actually run without any lubrication because of the Teflon base and the lead. Okay, there's that washer. Little stripe of grease, our needle bearing. Fill that. Now, since we've increased the stroke on this thing from roughly a 1/2 inch to 1 7/8 inches, we are going to want to crank this. The traditional single lip grinders only have about a 1/2 inch of travel, and I didn't like that. So I wanted longer travel because I'm going to be doing, you'll see in future videos, you'll be seeing where I'm doing cylindrical grinding on these, using these to reduce a boring bar shank or something. And I want to be able to traverse a long way without having to reclamp. Also, the way those single lip grinders are designed, you can't grind, once you loosen your lower rail, you lost your zero position, where by having a long stroke here, I can maintain a certain diameter and actually traverse across, do tapers or whatever that are longer than the little tiny travel. So I have a hole tapped here for my for a hand crank coming from McMaster car, and then I also have access holes here so that the socket head cap screws that hold this whole thing onto the base can reach through here, and I can have easy disassembly. This screw here is what actually does our preload, and this is where we put some pressure on the whole assembly. Let me grab my Allen wrench. This is where we actually put some preload on the whole thing, and that basically gives us a situation where we're locked in. And then we have 2 set screws, the original set screws, that go down in and bear on that relieved area that I had in the center there. So we'll snug these. So this is keeping the shaft from rotating. And then we'll adjust the preload. Okay, so now this is smooth. This is like just firm. Might be a little, I just want a little tension there. Yeah, this is like glass, just smooth as silk. And it's also rigid, meaning that when I'm cranking out here, this screw is not going to be doing this from bearing influence, because this is rigidly held. Those thrust bearings are very stiff, and this will be good and solid. So we'll just leave this sit right here adjusted. We'll tweak our screws here, lock up our actual grip on the shaft now. And and that thing's good to go. Yep, that's nice. So here's what I've made to hold the main nozzle. Just a piece of tubing that just happened to be the right fit for here. Gentle chamfer and blend angle here so that this doesn't bite in and grab and seats tight. A lock line reducer to go from whatever this is, half down to the smallest size. 3/8 end mill down in here to give an actual shoulder for this screw to hit. If you put that in there with just the tape, hit the screw hitting on the taper, it's liable to just swell out and cause issues. So I actually did the 3/8 end mill, which is just a little bit bigger than the head of an M5 button head. Ground part of this off into the actual radius of the tube, roughened up the tube with the belt sander, put some notches in the inside of this with a Dremel wheel so that the tendency for this to want to rotate and loosen would be minimized. And I used plastic welder epoxy. It's 4400 psi epoxy, really strong. So that just makes that so that this will stay put. And this will snap onto the tube that I have mounted here. I've drilled and tapped 2 holes for the threaded fittings here to go in permanent, and then this down here I've got this to snap on for the actual vacuum line, if I can get this thing on. Oh man, they're tight. Okay, so now this can go in, this can pivot, it can be pulled out quickly to get out to wherever it needs to go. Stick the hose in if I want to take it out quickly to do some other mount with it. I can do that, but we can get this in right into the business end here and suck that dust up right at the point of action. Done the same thing with the light. We've put a 90 degree on here. The light itself isn't bad on this thing. It's just that they had it on this super stiff tube, and there's no way you could bend it around to point in the right direction without it just springing right back. So this thing's actually got really nice intense light, and by putting the elbow here and using the larger lock line, this just lets this be put around wherever you want it easily.
I hope you found the content useful and interesting. If you did, please comment, share, subscribe, tell your friends. As I do other modifications and improvements to this Deckel Clone, I will certainly be posting videos, but there's no scheduled time span for that. Could be 6 months, a year, who knows. But I'll see you next time.